So initially I was going to have only 4 parts, but then part 4 was a little longer, so I have fifth part, is 5-part video. We were in part 4 where we were trying to build a realistic model of the movement of the paraglider, right? Thermaling in the air. And we said we'll get a very nice fit like that. Where we stopped was the following. We went through steps of conversions of the initial data set, and the last step, step number 3, was when we were conducting phase analysis, right? So we got the ratio of PC2 over to PC1, we got the arctangent of it, and we were saying that if we fit the linear regression over time, then that should give us the frequency of the rotation of this paraglider, right? And also the phase in the equations of the paraglider which we came up with. And interestingly, we got exactly that, right? So where is our in this equation, when we draw the arctangent, and you understand the tangent function is between minus pi half to pi half, so whenever tangent function sort of resets, we have to move it back. That's what I did here, right? So I'm just adding the phase, and when you do that, it almost perfect line fits into this movement with 99.77% r squared, and we were able to get the frequency and the phase, right? So once we got the frequency and the phase, it's interesting. We were able to get all the variables. Look in this equation, right? So x0 and y0 and speed of the wind, we were able to get from the initial step number 1 when we were converting. When we fit the linear regression into principal components of Cartesian coordinates. We got PC1 and PC2, and then simple linear regression gave us 3 coefficients right there. Then using some smart, not so smart, but using a trick here with getting the amplitude of the movement, we were able to get the radius, right, of the rotational movement. And finally, again, using phase analysis, where we got the principal components and we got some little like trigonometry and linear fit, we were able to get the phase and the frequency, and that gave us all the equations, and that gave us all the coefficients. Now we can just fit them into the equations of motions, and look, the orange line here is a fitted line, and the blue dots are the observations. It's not a perfect fit because the paraglider is in the air, right? The air is moving, so it's impossible to get exact movement, but look, the fit is pretty good, right? And the parameters are all summarized here in fit parameters, and I'm showing how the parameters were derived in each step, which I described. And then finally, once you got this sort of a fit, we can revert the steps. If you remember, initially I had principal component 1 and principal component 2, but they were on Cartesian coordinates. So from principal components, I can calculate my Cartesian coordinates and then get Cartesians and convert them back to latitude and longitude. And this final graph, this shows the Cartesian coordinates, right? So these are in kilometers, and y is also in kilometers, this kind of a fit. All right, and when we look at this kind of a fit, we can say, well, this speed of the wind is 4.3 meters per whatever the sampling interval was. If it was a second, then it was 4.3 meters per second. And then we see that the rotational speed of the paraglider was 30 meters over, again, whatever is the sampling interval. It says 30 meters per, I can't see the 30 meters per second. I think that's probably too much. Actually, I don't know how fast paragliders move. Maybe that's a second. Right, so and then once we get the meters, we can convert them, like I said, into latitude and longitude original coordinates, and when we do that, we get this plot, which I said I show you. It's a very, I think it's a very good fit right into the data. So that was what we did in terms of calculating the fit of a more realistic model. So let me maybe show a few things in Excel. So how I did that, right? So I have this data sheet where I just got the data, latitudes and longitudes, 123 observations. And in this sheet, I'm showing the first sort of naive orthogonal regression fit, which is shown by the orange line. It's already pretty good, right? This fit. It gives us a direction of the wind, by the way. This regression right there will tell you where the wind is blowing, right? It doesn't tell you much. It doesn't tell you yet about the speed of the wind, though. So that we will do in the sheet, which I called Cartesian. Like I said, in Cartesian, the first thing I did was in step 1, if you remember. What was step 1? Step 1 on the smaller screen, right? So the step 1 was to convert Cartesians into x and y's, and that's what I'm doing here. It's basically it's in kilometers. X and y now are in kilometers. I'm using radius of the Earth, and I'm using some trigonometry to convert Cartesian latitude and longitude, sorry, not Cartesian, but latitude and longitude in degrees. I'm converting them into radians and then into kilometers. So x and y are already in kilometers. I'm assuming flat Earth. Right, and then I'm again running the principal component analysis. I'm getting principal component vectors in Cartesian coordinates. Now, if you remember, in naive PCA, this was latitude, longitude. Here, it's again PC1 and PC2, but they're in Cartesian coordinates. This was principal component analysis I did using this eigenvector analysis, which we studied in principal components lecture. So PC1 and PC2 are the principal component vectors, right? Now I can, in my theoretical discussion, right, I drew also PC2 as a function of PC1, and that's what's going on here. So I just took PC2 and then just drew it as a function of PC1. It's a scatter plot with connected dots. Well, in this case, I already fitted the values. Right. Then the next step was what? We said, let's see, what was the next step? The next step was to do the fit, right? Well, the fits are in Excel. You can see here. Where's my fits? Okay, this is the fit, right? So this is a principal component 1, principal component 2. I just have the trend line, and from the trend line, you can divide the speed of the wind and then also the offsets of principal component 1 and 2. Yeah, this was principal component 2 as a function of principal component 1. Right, and then for amplitude analysis, again in Excel, it was rather easy, right? Here's my amplitude analysis. How did I do it? Well, I have my principal components, and then I detrended them, like I said in the beginning, right? So I detrended my principal components into PC1 and PC2 by removing what? By removing the slope here, right? So basically you remove the linear slope, and then it becomes your new PC1. And once you got PC1 and PC2, if I draw them over time, then they'll show as a typical sine wave rotational. So if you work with signals, you would see the sine and cosine, or imaginary and real parts, and so And this was my amplitude analysis, right? Remember I said, how do I identify R? Well, I get square root of the squares of PC1 and PC2. I get sum of squares and then square root of it, that's my R. And then if I get the average R approximately here, I don't have a trend, but why don't I just add the trend line here? Okay. Look, it's yeah, so it's a horizontal line, obviously, and the radius is I can't see it right here, but it's a pretty small radius here, right? Yeah. So then you get the average of this radius, and it happens to be what point? It's like a 6.6, 67 meters approximately, 0.067 kilometers, right? So that was my amplitude analysis, and then I'm calculating arctangents, right? Arctangent, and I'm showing it as orange line, and you see it's like a zigzag. Why? Because it loses the phase, not phase, and I have to add the phase back, and that's what I'm doing here. Every time it sort of clips up, I'm adding a phase. And when you do that, you get this blue line, which a linear trend line fits perfectly. And that's how I got all my parameters, right? I through just using linear regressions and some trigonometry, I got all the parameters which I need, and I highlighted them in yellow. I got the frequency in the movement equation, right? In this movement equation, I'm showing in a smaller screen. In Excel, I was able to get all the parameters: frequency, phase, wind speed, radius of the rotational movement, and x0 and y0 are principal components means, right? Shifts. Once I got all of those, now I can generate actually my x and y's. Oops, sorry, in Excel. It's x and y's. These are my Cartesian coordinates, and then I can draw them now as a predicted line here. So this is my orange is a predicted spiral in Cartesian coordinates. And using these Cartesian coordinates, I can convert them back into latitude and longitude. And when I do that, I get this nice fit line. So that was it. If you're taking my course, then you will get this Excel. If you're just watching it in YouTube, then you do not get this Excel. But you can reproduce it. I think I gave enough instruction here for you to reproduce everything. Again, what we did in part 4 and 5 was we tried to build a realistic model. We tried to follow the statement I made that what was it in part 3, right? Second, like a part 3 was all about that model should match DGP, and that's what we tried to do in part 4 and 5. We tried to build a model, simple model, of course, right? But although it is simple, it reflects the underlying physical process of that paraglider moving in the thermal much better, or quite closely actually, to the actuality. It turned out that the radius was pretty close, right, to a constant. It wasn't exactly the constant, right? It seemed to deviate a little bit here and there, but it was pretty constant, about 67 meters or so. And the wind speed was probably also about constant or something. So we could improve this model, right? We could maybe relax these assumptions of the constant radius and wind and so on. But this is the kind of a model you build when you understand the underlying process and try to reflect it in your equations, in your model equations. And when you do that, you have much better success than when you're just trying to throw some mindless regressions, which unfortunately a lot of us do in when data mining, or when we don't really understand the phenomena, but we want to produce some sort of forecast. And this was it. This was the end of the module. Thank you.